Picture this. Ancient Greece, around 400 BC. Two philosophers, Democritus and Leucippus, are pondering the nature of matter. They propose a radical idea that the universe is made up of tiny, indivisible particles, which they call atomos. This is the birth of atomic theory, but what exactly did they mean by atomos? Democritus and Leucippus envisioned these tiny particles as solid, indestructible, and eternally existing. They believed that these particles moved around in a void, combining and recombining in different ways to form the diverse world we see around us. Each atomos, they said, had its own unique size and shape that determined the properties of the material it formed. Even though their ideas were speculative and lacked experimental proof, they laid the groundwork for the concept of atoms. Fast forward to the Roman Empire, where the atomic concept found a champion in the poet-philosopher Lucretius. He penned the epic poem De Rerum Natura, or On the Nature of Things, preserving and transmitting the ideas of Democritus and Leucippus. Through his vivid verses, he painted a picture of a world made up of atoms and voids, drawing the attention of thinkers to the atomic concept. But as the Roman Empire fell, so did the focus on atomic theory. The Dark Ages saw a shift in scientific discourse, where atomic theory took a back seat. This period was marked by a lack of scientific progress and a focus on religious and philosophical ideologies. It was a time of stagnation for atomic thought. So the seed of atomic theory was planted in ancient times, but it took centuries before it began to sprout. Fast forward to the 18th century, the era of enlightenment, when a man named Antoine Lavoisier laid the foundation for the atomic theory's revival. Lavoisier, recognized as the father of modern chemistry, introduced the concept of elements, substances that couldn't be broken down further by chemical reactions. He also formulated the law of conservation of mass, stating that matter can neither be created nor destroyed, only transformed. This pivotal idea sparked a renewed interest in atomic theory, leading us to our next scientific pioneer, John Dalton. Dalton, an English chemist, proposed the atomic theory in the early 19th century. His theory posed that all matter is composed of tiny, indivisible particles called atoms. He suggested that atoms of a specific element are identical in mass and properties, and atoms from different elements have different masses and properties. Dalton's theory was revolutionary. But, as we know, science never stops questioning and exploring. Enter the 20th century, a time of rapid scientific advancement. J.J. Thomson stumbles upon a new particle, the electron. Using a cathode ray tube, a simple piece of equipment that shoots rays from a negatively charged electrode to a positively charged one, Thomson discovered that these rays were composed of tiny, negatively charged particles, electrons. This finding shook the scientific community, challenging Dalton's theory of indivisible atoms. It led to the creation of the plum pudding model, where the atom was pictured as a positively charged sphere, with electrons embedded within like plums in a pudding. But this wasn't the end of the atomic adventure. Enter Ernest Rutherford, the man who would revolutionize our understanding of the atom yet again. Through his ingenious gold foil experiment, Rutherford discovered a concentrated, positively charged nucleus at the center of the atom, with electrons whizzing around it in empty space, leading to the nuclear model of the atom. Rutherford's discovery turned the atomic world upside down, but there was more to come. Now, imagine an atom as a mini solar system. That's what Niels Bohr did. Bohr's atomic model was a game changer. He proposed that electrons move in fixed orbits around the nucleus, much like planets around the sun. But these orbits, or energy levels, contain only a certain number of electrons. This model helped explain why atoms absorb or emit light, a phenomenon that previous models couldn't quite nail down. But the atomic universe didn't stop expanding there. After Bohr, scientists discovered even tinier particles within the atom. The neutron, with no charge at all, and the proton, positively charged, joined the electron in the atomic family. And then came quantum mechanics, a field of physics that deals with phenomena on a very small scale, like atoms and subatomic particles. quantum theory suggested that these particles can behave both as particles and waves, adding another layer of complexity to our understanding of the atom. And so, our understanding of the atom continues to evolve, much like the universe itself. So, what's the takeaway from our atomic voyage? Simply put, the atomic theory, from the ancient Greeks to quantum mechanics, evolves relentlessly, propelling us deeper into the mysteries of matter. Thanks for joining me on this atomic adventure. Don't forget to subscribe for more scientific explorations.